Hey everyone, and welcome back to The Explainer. I'm Ricardo Torbillo, and today we're going to tackle a real classic physics problem, the electric field of a charged ring. Now, I know it sounds a little intimidating, but trust me, with the right strategy, we're going to see it all click into place. And, our source material really hits the nail on the head here. It calls this a classic and excellent exercise for understanding how electromagnetism applies to extended objects. And that's exactly how we're going to approach it, step by step. All right, let's dive right in. First up, the problem of the ring. So the big question we need to ask ourselves is, why can't we just use that simple go-to formula for the electric field we all learned? Well, the answer really boils down to this. Coulomb's law. The famous E equals kq over r squared? That's perfect for point charges, when all the charge is crammed into one single spot. But with a ring, the charge Q is smeared out. It's spread all along an extended object. And that changes the whole game. So, if the charge is spread out, how do we even talk about it? We use something called charge density. You've got a few flavors, volumetric for 3D things, superficial for 2D areas, but the one we care about today, the one that's going to be our hero, is linear charge density, or lambda. It's just charge per length, which is absolutely perfect for things like wires and, you guessed it, our ring. Okay, so that brings us to our game plan. How do we attack a complex problem like this one? The secret is to think small. We're going to break this big, complicated problem down into a bunch of simple, manageable little pieces. And this strategy is a beautiful 3-step process. First, we divide. We chop up the ring into an infinite number of tiny, infinitesimal pieces of charge, which we'll call dq. Each one is so small, we can pretend it's a point charge. Step 2, calculate. We figure out the tiny bit of electric field, dE, that each little dq creates at our point of interest. And finally, step 3, sum. We add up, or, integrate, the electric fields from all those tiny pieces to get the grand total. So, divide, calculate, sum. Simple, right? But hold on. Before we just jump into the math and start integrating like crazy, we're going to use a super powerful trick. I like to call it the magic of symmetry. Seriously, this is the clever shortcut that's going to save us a ton of work. So the question we've got to ask is, can we actually simplify this problem before we even touch the calculus, before we do the integral? And the answer is a big, resounding yes. Okay, now this is where the magic happens. Let's look at opposite sides of the ring. Imagine a little piece of charge, dq, at the very top. It creates an electric field that points kind of up and to the right. Now look at its partner, the piece of charge directly opposite it at the bottom. Its field points kind of down and to the right. See what's happening? The horizontal components, the sideways bits, they point in opposite directions. They completely cancel each other out. But the vertical components, the bits pointing along that central axis, they both point in the same direction. They add up. And this happens for every single pair of opposite points all the way around the ring. So what's the incredible result of all this? The net electric field can only exist along that central vertical axis of symmetry. Everything else just cancels itself into oblivion. I mean, how cool is that? We just used pure logic to make half of our math problem completely vanish. All right, with symmetry as our trusty sidekick, we're finally ready to get into the math, and you're about to see just how much simpler those calculations become. So remember, the field from one tiny piece dq would normally have two components, but we just proved that we only care about the vertical part, which we call dEz. Now, from basic trigonometry, we know that to get that vertical component, we just need to multiply the total field dE by the cosine of that angle, alpha. And if you look at the geometry of the setup, the cosine of alpha is just the adjacent side, z, over the hypotenuse, r. So when you put it all together, our vertical component dEz is just the basic field formula times z over r. Okay, next step. To get the total field, we have to add up all of those little dEz contributions from every single dq all the way around the ring. And what's the mathematical tool for summing up an infinite number of tiny things? You got it, it's an integral. So we set it up, And yeah, I know it looks a little bit scary at first glance, but don't worry, it's not as bad as it looks. And here comes the most satisfying part of the whole calculation. Take a look inside that integral. Almost everything in there is a constant. The value k, the distance z to our point, the ring's radius r, none of those things change as we move around the ring. So what can we do? We can pull them all right out in front of the integral. And what are we left with inside? Just the integral of dq. And what's the sum of all the tiny little pieces of charge? It's just the total charge, q. How elegant is that? So we put all the pieces back together, substitute our constants, and there it is. The final formula for the electric field of a charged ring along its central axis. It's just a beautiful example of how calculus and symmetry work together to give us a really powerful and, honestly, quite elegant result. So, we've got this nice-looking formula, but does it actually make sense in the real world? Is it physically reasonable? To find out, we need to do what I call a reality check. We're going to test it at the extremes. Let's check two limiting cases. First, what if we go really, really far away from the ring so that our distance z is way bigger than the radius r? Well, in that case, the r squared in the denominator becomes pretty much negligible, and our big complex formula simplifies down to, you guessed it, the formula for a point charge, which makes perfect sense, right? From far away, a ring should just look like a dot. Okay, now for the other extreme. What happens right in the center of the ring, where z is 0? Well, if z is 0, the whole numerator becomes 0, and our formula tells us the electric field is 0. Again, this is exactly what we'd expect. Right in the middle, the perfect symmetry means every piece of the ring has an opposite piece that cancels its field out completely. And our source material puts the physical intuition for that first case perfectly. It says, from far away, the object looks like a single point in space where all its charge q is concentrated. At a distance, the actual shape of the ring just doesn't matter anymore. So, there you have it. We've cracked the code for the charged ring. We saw how the logic of dividing, using symmetry, and then summing it all up not only gave us the answer, but also passed our reality check. And that really leads to a fascinating final question, doesn't it? Now that we understand the ring, what's next? A disk? A sphere? Does this powerful logic of symmetry and integration still apply? Well, that's something for you to think about in your future studies. Thanks for joining me, and I'll see you on the next explainer.